Data and Math, more finite field symmetry. In the first video in this series, I mentioned briefly that I began this journey after implementing a Reed-Solomon-Vandermonde error correction system. I was able to implement this system and validate it through testing, but I didn't understand it completely. At the time, I was working at a software company that dealt with an enormous amount of data. Data integrity was the life or death of the company. That also was the cause of their interest in an ECC system, but they were not interested in relying on a system that wasn't perfect in every way. Seeing as I was not a mathematician, it made sense to hire one, so he could validate the math behind what I was doing. They hired a math PhD to review the code I had written. After some time, they reported that it worked, but they weren't quite sure why. I was shocked, although since that time I've discovered just how specialized this kind of mathematics is. In this video, I'll tell you why it works. The Vandermonde Reed-Solomon method uses a matrix that is constructed by performing column operations on the power table. The matrix should be rectangular in the vertical proportion. We reduce the topmost square to an identity matrix, allowing all the operations that we perform in the column to affect the bottommost rows. As a side note, I'll be listing my matrix right to left. It's a bad habit I picked up when working on math with a pencil and paper. I put my symmetry on the right and my problem on the left, and they grow as needed to the middle. When I first implemented this method, I did so over a finite field. So the result was gibberish. However, if you're paying attention, you'll notice that this is the same result we get when dealing with our function signatures. Essentially, we're performing this same action when we extend a number triangle vertically from the rightmost column to the left. Let's look at this a little bit more closely. The matrix on the left is the same one that we're creating through our number triangle operations. Extend the furthest most column, work backwards, and voila. Here we're looking at the polarized Pascal triangle. However, like we discovered earlier in this series, we don't have to use the polarized Pascal triangle if we solve for something other than identity. Also, the Pascal triangle is only present in the first row that isn't part of the identity matrix. You'll recall that if we use the symmetry defined by the top of the number triangle instead of its left side, that we actually achieve a more simple solution. Let's look into that a little further. Here's the identity form, and here's the Pascal form. If you'll recall, when we're not using the Pascal form, we have to actually use a function to discover what rows further down this matrix are. However, in the Pascal form, we can simply use excerpts from the Pascal triangle. This is a huge win for simplicity and also performance when it comes to implementing this algorithm. So here's what the matrix will look like as we work through each step. We're actually doing precisely half the amount of work to generate this matrix, compared to the other identity method, that is. We also have the advantage of not introducing negative numbers into our symmetry. Summary. Column matrix transformations of the power matrix to an identity matrix converts all the extra rows to truncated rows of the polarized Pascal triangle. Converting it to the Pascal identity gives us truncated non-polarized Pascal triangle rows, a better symmetry. It works, but do we know why? Yes, because the Pascal triangle is the origin of function symmetry, and the number triangle embeds it. Due to the properties of a finite field, the Pascal triangle behaves somewhat differently. When we attempt to construct a number triangle over a finite field, the symmetry becomes the binary Pascal triangle, or the Pascal triangle mod 2. In a finite field, when constructing a number triangle, due to its limited properties of arithmetic, we will always construct a symmetry that is the binary Pascal triangle. The reason why the Reed-Solomon-Vandermonde method works over a finite field is because the column reducing effect that we explored earlier generates the Pascal triangle for that finite field, one that is not limited by the limitations of the arithmetic in that finite field. It also is not intuitively recognizable. When we look at a Reed-Solomon-Vandermonde truth matrix, it doesn't make sense. But what we're actually looking at is the Pascal triangle for that finite field. The Pascal triangle symmetry is what causes functions to work. The Reed-Solomon-Vandermonde method is simply executing a function in a finite field. This is a simple yet very exciting discovery. It opens the door to so much more that we can do. This lets us define what a pattern is in a finite field. Since patterns in a finite field are no longer controlled by 0. We'll explore this in future videos, as well as many other principles that have arisen in this video. Namely, what variations of the Pascal triangle exist, and what rules define their construction. What happens if we, say, create a finite field that uses, I don't know, the Pascal triangle mod 3 for its arithmetic? I also like to use this principle in the inverse. I can tell how well I've solved a problem by how many new concepts arise and how many doors there are to explore. Web Demo and JavaScript API available at math.d8data.io.